Hello and welcome. In this video we're going to investigate what's known as Euler's method. And we've already looked at some approaches for solving differential equations, including separation of variables, and we've looked at qualitative techniques that help us investigate or understand the solution to the differential equation without actually having to solve it. Now oftentimes we're doing these things because the differential equation is not solvable, or because we just want some simple information without too much detail. So we can resort to things like slope fields, get a good sense of how the solution behaves. We can do an equilibrium analysis. However, perhaps what we want is some numbers. We want some values of y for different times. So let's think about this fact. In order to generate actual pairs or estimates of pairs that would be on the solution function, so let's imagine that for the moment we basically know what our initial condition is at time 0. So we have some 0 comma y of 0 ordered pair. We know that value, and what we want to do is maybe the exact solution looks like this. But what we want to do is we want to generate some estimates at different points in time. So maybe we use some technique and we estimate an ordered pair that is there. Now clearly that's not on the actual solution curve, but it is an estimate. And then at the next time value I estimate another one, and perhaps what I find is that my estimates are off, but they give me a sense of data. They give me the ability to manipulate some numbers. So maybe these are my estimates. And from those estimates, I want to get a sense of how this actual solution, y of t, behaves. And we can use this idea to generate estimates for these different pairs for some interval of t. So maybe typically we want to go from time 0, in this case up to time, looks like time 3. We wanted to estimate the y value at time 3. Thus we're utilizing what's called a numerical method. And a numerical method is just a method that gives you actual estimates of the solution. Qualitative method did not do this. It told us how the solution behaved. The slope field showed us how the solution flowed, where it went, whether it increased or decreased for different initial conditions, but we have yet to actually approximate solution values. So we're not going to actually build the solution function. We're going to build a bunch of ordered pairs that we hope to be very close to that function. To exploit this fact, let's start off with this ELK model. We have the rate of ELK per year being 20% of the number of ELK, so that's our reproduction rate. Another way of thinking about this is each adult female ELK produces, or every adult ELK on average produces 0.2 ELK as offspring. We can create a table like the one below. We can calculate the slope at each point, and we can then use these slopes to predict the next value of y. Suppose our initial condition is a y of 0 equals 10. So we can see that if we have 10 ELK, the rate of change of ELK per year is going to be 2. And in this table down here we can see that more clearly. So we have in our first row, we're recording that at time 0 there were 10 ELK. That's a given. We need that information, along with how the rate of change of ELK occurs. And that's at a rate of 20% of the current number of ELK. So at time 0, when there are 10 ELK, this equation only relies on the value of y. It doesn't matter whether it's 1998 or 2025. 20% of the 10 comes out to 2 ELK per year. Now that's a positive number, and we should really make note of the fact that that's a positive number, because that tells us that the number of ELK is bound to increase by 2 ELK per year. Now this could be thousands or hundreds of ELK. So what happens here is 1 year passes. And since 1 year passes, and we're saying that according to our current information, we expect to gain 2 ELK over the course of 1 year. This is always going to be in units of ELK per 1 unit of time, or units of y per 1 unit of time. And the reason that is because if you put this over 1, now that's the numerator represents how many ELK, which is 10, per 1 year. So 1 year passes, which means I should gain 2 elk. So I started off with these 10 elk. I've gained 2 more over the course of that passing of 1 year. Therefore, now I have 12 elk. I can repeat this process now. So now I've come up with an estimate of the number of elk at time t equals 1. Okay, so at t equals 0, we said that there were 10 elk. Maybe I'll count in fives. 5, 10, 15, 20. So there were, at time 0, 10 elk. Now I assumed that 2 elk per year is a constant rate of change. So to get 12 elk right here, what I should draw between these 2 points is a straight line. And the reason I'm doing that is because this 2 elk per year is assuming a constant rate of change over the period of that full year. Now that is a simple way of thinking about it, but it also poses the problem of, doesn't the rate of change continuously? And when we're dealing with calculus, we know that the rate of change is just instantaneous, but we're treating it as if it were constant. So we just went from knowing the point 0, 10, and we just estimated the point 0, 12. I'm sorry, not 0, 12, but 1, 12. 1, 12. That's our new data value. So we're building points on this solution. Now, this is going to be wrong because inherently we just assumed a constant rate of change for any period of time. And for any period of time, the rate of change is not actually constant. So the new dy dt is now going to be bigger because now there are more elk reproducing. And so 20% of 12 is going to give me 2.4. And we're not going to round that. We're just going to assume this could be hundreds of elk, millions of elk per year, whatever. So now 1 more year passes. We get plus 1 year. And we expect to have 2.4 more elk if 1 year passes, and it did. So we have the original 12 elk from time 1, plus the gain in elk of 2.4, which gives me 14.4 elk. And now I'm going to repeat this process. Now here we are at time 2. Okay, so time 2, we now have 14.4 elk. So a little bit greater of a jump. Notice that our rate of change got bigger. So now this line segment is a little bit steeper. And this point here is the point 2, move it over a little bit. Let's clean this up just a tad. So this was 1, 12. And now we're up here at, right about there, 2 and 14.4. And now we can again compute the new rate of change, which again is going to be bigger because now we have more elk reproducing. And 20% of 14.4 comes out to 2.88. And the more decimal places we keep, obviously the more precision we have. But the same kind of notion moves on, that now we're going to add that to 14.4, and we'll have 17.28 elk. So at time 3, we now are up here at 17.28. Notice that that rate of change, I'm exaggerating this, but it got bigger. And now we're at time 3, and we have 17.28 elk. We repeat the same process one more time because we want to estimate how many elk there are at time 4. So we'll take 20% of 17.28. And 20% of 17.28 is about 3.46. So notice again our rate of change jumped, and now if we take how many elk we had at time 3, plus the fact that we expect to gain 3.46 more elk, that's going to give us 20.74. 20.74. And so at time 4, we're up here at 20.74. And so now we have our estimate at time 4. We would say that we expect that at time 4 we will have 20.74 elk. And there is our estimate. Now, how good of an estimate is that? We don't know right off the bat, but fortunately for us, we know that this is a separable differential equation, and we can go about solving that. So the actual solution that we'll get is 10e to the 0.2t. So you can go ahead and try to do the separation of variables on that, see that that's what you get. and below are the actual values of y. So the thing that we notice about our estimates is that, first of all, here initially, if we compare time 0, those are the same, because that's a given, so that's not anything we're estimating. At time 1, we estimated 12 elk, but in actuality there were 12.21. This is the disadvantage of assuming a constant rate of change, because the rate of change is actually getting increasingly larger. So if we looked at time 1/2, it would no longer be a rate of change of 2 elk per year. It would probably be somewhere along the lines of 2.2 elk per year. So at time 2, we estimated 14.4. The actual value is 14.92. So notice that not only do we still have error, but the error just got bigger, because we were off by 0.21 at time 1, but at time 2 we're off by 0.52. And time 3 we estimated 17.28, but the actual answer was 18.22. So we were off by about 0.94 elk. And then by time 4 you can see we're approaching about 1.5 elk off. So we underestimated all the way up until time 4 compared to the actual solution. And one of the things we should keep in the back of our minds is we often don't have the actual solution to compare this to, so we're going to have to figure out how do we know that we're close with this estimation approach. So how do we improve this estimate? Well, one of our inherent flaws here was that we were assuming a constant rate of change, and that's going to be wrong no matter what. But I can reduce the amount of error by assuming that the rate of change is constant for a shorter period of time. But before we do that, let's take a look at the two plots. The blue plot here is the exact solution, and that is the function, comes from the function y of t equals 10e to the 0.2t. This is our approximate solution. And this is with, I'm going to write this, I'm going to say delta t, the change in time that we perceived was 1 year. We made our estimates 1 year apart. So we looked at time 0, so notice both of our points are at 0, 10. But then at time 1, we made our first estimate. Time 2, we made our second estimate. And we can also see that this error is really small at first, but it grows to be sizably larger as we move on. This is called compounding error. The reason we're compounding error is because we're using a wrong value, and with that wrong value, back here, this value was wrong, we're using that to calculate a new rate of change, which is wrong, and then we're combining those two to produce another value, which is wrong again. And then we're using wrong values and making wrong estimates with them. Now, we're not that far off, but you can see how this thing will blow up as we start to develop this for further time. One way to improve these estimates is to assume a constant rate of change for a shorter period of time. That is, we assumed our slope was constant for delta t equals 1 year. What if we updated our slope every half a year? Well, if we did that, we have to be a little bit cautious, because remember that dy dt, as we said earlier, is per 1 unit of time. So this is still 2 elk per 1 year. But notice that the time advance here, the time step, or the step size as we call this, is half a year. So if this is a ratio of 2 elk per 1 year, my change in y is not actually going to be 2. My change in y is going to be my step size, which is half a year, and I'm going to multiply that by f of ty. Now remember, another way of saying this is just, this is dy dt, but the reason I write it as f of t comma y is because it allows me to actually specify the t and the y that I'm positioned at. So here I'm looking at f of 0 comma 10, and in other words that equals half a year times 2 elk per year, right? So if I only change time by half a year at a rate of 2 elk per 1 year, then that comes out to 1 elk. That's my change in y. Notice that the years are gone now because the years cancel out, and I'm now left with just a gain of a change in y of 1 elk. So instead of now taking 10 plus 2, I'll only do 10 plus 1, which equals 11. Again, that's only half the time, so I should only gain half the elk. Now I'm going to repeat the same process. I'm going to calculate 20% of, but now it's going to be 11. That's going to be 2.2 elk per 1 year. Again, that's 2.2 over 1. So to calculate the new slope, what I have to do is take my time step, which is half a year. By the way, these time steps shouldn't ever change abruptly. You should settle on a time step and stick with it all the way through. Otherwise, you get weird compounding of errors. Now that's half a year at 2.2 elk per 1 year. So my change in elk will be 1.1 elk. Again, my years cancel out. Beautiful dimensional analysis here. So I expect to change y by 1.1 elk. We're at 11, so we're going to add 1.1 to it. That's going to give us 12.1 elk at time 1. And you can already see that our estimate here is 12.1 elk at time 1, whereas when we did 1 year at a time, our estimate was 12 elk. The actual answer at time 1 is 12.21 elk. So you already see that our estimate at time 1 is a little bit more precise. Now, of course, I'm going to repeat this process. I'm going to repeat this process many times. So rather than to continue writing this out, I hope that you get the sense of what's going on here, but continue to work this out. What we should get is 13.31, 14.64, 16.1, and so on. And at time 4, we get an estimate of 21.44. So the key here is whatever your step size is, that's the factor by which you need to scale your slope so that you get the number of elk that you're expected to gain just over that shorter window of time. So if this was 1/10 of a year and we went 0, 0.1, then this would be 1/10 of a year change times 2 elk per 1 year, and that would mean we would only expect to gain 0.2 elk. All right, so I encourage you to fill out this table, verify this. But here are the 3 graphs once again, and you can see that on top we have the exact solution. So this one is the exact, and that once again was y of t equals 10e to the 0.2t. Down here we had the estimate for delta t equals 1/2 a year, and I'm sorry, for delta t equals 1 year. And you can see that the little x's occur, our new estimates occur every 1 full year. The purple curve here, you can see that there's still straight line segments, but every time 1/2 a year passes, we get a brand new estimate. So this purple point here is an estimate for a half marker, whereas in the green graph, we did not estimate that. So let me find my closest to a purple. There we go. This is purple. So this is estimate for delta t equals 0.5 years. So you can see that the tightness of our error is getting better. So we have a lesser error here. Still, that error is growing, so that should be alarming to us. It's still getting bigger as time passes, but it's not quite as big as, for example, here we saw that this error was much larger. I'm just putting that a little to the left so you can see the distinguishing lines. You can see that we've about cut the error in half, if not a little more. So clearly there's a direct trade-off between the step size, so that's the name of this delta t, and the precision of the estimates. As we make delta t smaller, we get closer to the exact answer, as evidenced by the spacing between our exact curve and our estimated curve. But on the other hand, as we make delta t smaller, we increase the number of computations, right? We had to double the number of computations in order to cut the time step in half. We had to basically make our table a lot larger. We had 1, 2, 3, 4, 5, 6, 7, 8 time steps, whereas here we only had 1, 2, 3, 4 time steps. So we gain precision, but we increase the number of computations. For Euler, back in back in time, I'm not going to give you an exact year because I don't know exactly, but there were not computational devices that were efficient enough to sort of break up this trade-off. Now with computers, and computers being as fast as they are, making the time step really, really small does not add too much load on a computer. But that being said, if you make this time step really, really small, like 0.000000001 or 1 times 10 to the negative 20th, it's going to put a strain on any computer. So let's think about, before we actually allow technology to take over for us, let's think about what this process looks like. So if we were computer programmers, we would know what we need. Well, we need a differential equation, something that gives us the rate of change, because that's what we needed in order to make time steps. We needed some initial condition. I didn't say initial here because we don't have to start at time 0. We could start at time 5. By the way, if you start at a different time other than 0, that's called a boundary value problem instead of an initial value problem. The next thing we did is we calculated the change in y for a time step of 1. Remember, delta t was 1, so all we had to do is calculate the slope. But if our time step is half, then we need to scale the change per 1 unit time by whatever our change in time is. And then now we calculate the new y value. So visually speaking, that the y value of that next ordered pair, we got that 14.4 by taking the current y and adding the change in y to it. And then we also had to increment time by its time step. So those two processes are described here in steps 3 and 4. So the next y value is the previous y value plus the change in the y. The new t value is the current t value plus the change in the time. So now we have the ordered pair. We put these two values together. We have that new ordered pair that we can now graph. We repeat this cycle from steps 2 through 5. We loop this enough times to get to our final ordered pair. Whatever our stopping point in time is, we continue doing this. So these steps 3 and 4 can be thought of more generally as to get the next time, a next t value. So t of k plus 1, that just means 1 time unit later. It doesn't have to be plus 1 year. It could be just t1 could be half a time unit later. So we're going to take the most recent value of time, increase it by delta t. So for example, if right now we're at time 0 and our time step is a half, so if this is right here is t0 and I want the next time step, 0 plus a half will give me 0.5. So back here at our table, we could think of this as being t0, t1, t2, t3, t4, t5, t6, t7, t8, and this says y0, y1, y2, y3, y4, y5, y6, y7, y8, and so on. So notice that these subscripts do not actually denote what value the time is, it just denotes the current time step. And delta y, recall, is given by calculating the slope, the rate of change per 1 unit time, and then scaling it by whatever our change in time is. Now, this is going to get much more tedious. We often don't want to stop at time steps of a half. We really want to go in tenths, hundredths, thousandths, etc. Now, there are many calculators out there. You can write a MATLAB program to do this for you. You can write a Python program to do this for you. One way to do it is through wolframalpha.com, and what you would type in is if we wanted to look at the estimates for a certain point in time, we would type in the following into wolframalpha.com. Use Euler method, and then you could write dy/dt, but y prime is just easier to type, equals our function 0.2y, comma, our initial condition, y of 0 equals 10, comma, from t equals 0 to t equals 4. And then we list our step size, ignore that little vertical bar, that was just my screenshot, my cursor was there, comma, h equals 0.01. Now h and delta t are the same thing. Some notations use the h, some use delta t. And so here you can see it says solve that differential equation using Euler's method with a step size of, and then this is kind of funky, but you can ignore that. And here's the table that you get. Now notice it's a truncated table because this is going to require 400 computations after time 0. So step 1, it's going to calculate for time equals 0.01. Step 2 will be for t equals 0.02. And so there's going to be a lot of computation in here, but all we really care about is the 400th line, which gives us the estimate for y at time 4. So here our estimate is y of 4 is equal to 22.2376. And you can see that that estimate for that time step, our exact value was 22.26. We're coming up with an estimate of 22.2376. So our error, if we want to look at the amount of error, this is going to be our estimate minus our exact 22.26. And the difference between those two values is negative 0.0224. Now I do want to do this subtraction as the estimate minus the exact. And the reason I want to do it in this order is because I can see whether I'm above, my estimate is above or below. So what this means here is that we are below, our estimate was below by 0.0224 units. If you subtract them in the opposite order, you'll still get the same value, ignoring the sign, but the negative just tells us that we've underestimated by a little bit. So you can see that's not very much, right? That the amount by which we're off is not very much. Now we can do the same thing for y prime equals 0.2y, but just changing the step size to 0.001. And you can see that now our estimate, and our rounding is kind of sloppy here, so let's just ignore the rounding for just a moment. I'll round this to 3 decimal places, 22.254 minus our exact, which is 22.26. 22.254 minus 22.26 is negative 0.006. So once again, notice that we did the estimate minus the exact, and notice that we're still below, but we're below by an even lesser amount than we were below by when we had a bigger step size. Just to show you what this looks like, when you're actually typing this all in, it even shows you some information down here, some stuff you probably don't need to look at. If you're interested and you want to find out what this stuff is, you can do some research. But notice that it shows us a comparison of the exact and the numerical solution. One's in like a purple and one's in a blue. You can't see it here because we're almost exact for all the way up to time 4. So see, here's our t-axis, our estimate of y. So we're doing really well here with that small of a step size. But if I change this to h equals 1, what I should immediately notice is that my graph is going to show the estimate and the exact as being quite far apart at time 4. Okay, so you can see that this is just what we saw in our graph that we built numerically. And in this case, it shows me the whole table. If you do a smaller step size, it'll by default just show you the portion of the table that it finds most relevant. So these sometimes do take a second. So you see that it just shows us time 0 and time 40. If you press more, it will actually blow up that table a little bit. So here you have it. If you press more, it'll expand it a little bit more if you press it again, but now it shows us every second time step. And if we show even more, it'll show us the whole table. Now, just a caveat, if you do this too many times, it's going to sometimes really lag in trying to produce the whole table. You can see there it all is if you want to compare. But you can see that with a step size of 0.1, our exact and numerical solution are really close. Okay. So the other thing, right now we've looked at absolute errors, and an absolute error is the amount by which our answer is above or below the exact answer. However, this is not a very good metric. It's not a very good measurement because a difference of 0.1 may not look like much, but it all depends on what it's relative to. So if you look at a difference of 0.1 between the numbers 1000 and 1000.1, we can probably all agree that that 0.1 is not a big difference from the 1000. But it is a large error with numbers that are in, say, tenths, like 0.1 and 0.2. Those are 50%. That's a 50% error there. If we wanted to get 0.2, but we ended up with 0.1, we were 50% under, and that's a huge relative difference. So to get the relative error, notice that what we do is we still calculate the difference between the values. That is our estimate minus our exact, just like we did here. But then we take that error, and we divide it by where we should be, and multiply it by 100 to get percentage. This will just give us a decimal, but multiplying by 100 will convert it to a percent. And we'll be able to see how far, by what percentage we are under or over. So in our estimate with delta t equals 1, our absolute error, now remember at time 4 the exact answer is 22.26. Our estimate for time 4 with a step size of 1 was 20.74. And that's about 20.8. I don't know why I rounded to that value. 20.74 minus 22.26 means we're about 1.46 units under. So now we take that absolute error and we divide it by the exact value, which is 22.6, multiply it by 100, and we are below by 6.6%. That's fairly sizable. 6.6% error is pretty big, even though the number itself isn't big, but it's big relative to the actual answer. Now, if we look at time step of a half, our estimate for time 4 was 21.44 elk. The exact solution doesn't change because we changed the time step. It's still 22.26. And now we were only below by 0.82 units. When we divide that by where we should have been and multiply by 100, we're only under by 3.68%. Now that's not exactly, just because we decrease the step size by a half doesn't mean we decrease the error by exactly a half. It's a little bit more complicated than that. But if we take the step size down even further to 0.1, where our absolute error was negative 0.0224, I'm sorry, this was 0.01. That was 22.24 minus 22.26, which was about negative 0.02. Divide that by the exact value, we get negative 0.09%. You can see we're really getting super close to that exact solution. And now with the step size of 0.001, we calculated the absolute error as negative 0.006, which if you rounded to the hundredths place is negative 0.01. Divide that by 22.26 and multiply by 100, you get negative 0.05%. And you can see that as we decrease the step size, we are indeed, as we pointed out, as one of the trade-offs, we get closer to the exact answer. But notice that it took 4,000 computations to get there. So if we were doing this by hand, it would clearly be impossible. Oh, I shouldn't say impossible, but unfeasible. Okay, well, you notice that we were under with our errors here. It's not always the case that you're going to be under. It really just depends on the differential equation solution. Our solution was an increasing exponential function, so we were constantly underestimating because we were using slopes as being constant, but the slopes continue to get bigger. If a function even oscillates, we may undershoot over some intervals and overestimate in others. And lastly, let's take a look at a major flaw with this approach. So we said initially that this approach is specifically for situations where you cannot find the solution using an exact method. Now, obviously, the one major flaw with this is that it's clearly prone to error. And no matter how small our delta t is, after enough time, that error is going to continue to compound. We use a numerical approach because we cannot find the exact solution with some analytic method. So if we are estimating a truth we do not know, how can we assess how close that estimate is to the exact solution without a comparison? One way to approach this is to not compare exact to estimated, because perhaps we don't have exact, but to compare estimated at one step size to estimated at another step size. So we already know that as we decrease the step size, our approximations get more exact. So that means that if I compared my approximation at time 4 at delta t equals 0.1 to the estimate at time 4 of delta t equals 0.01, and I noticed that my y value changed by a lot, then that clearly means there's a big difference in the two estimates. However, if that error between these two values, that difference is very small, then it seems that decreasing the step size is no longer improving the estimate by much, and we may thus assume that we are converging in on the exact result. So consider another example, the differential equation dy dt equals 0.2y minus t. Now we don't know how to solve this. This is not separable, but we want to estimate the value of y at time 10. So we compute the estimates at t equals 10 for delta t equals 1, delta t equals 0.1, delta t equals 0.01, etc., and compute the relative error from estimate to estimate. Suppose we want the relative error to be smaller than 0.9%. What is that estimate? What are we going to go with as our final y of 10? So I can't always just default to the 0.001 step size, because even that small of a step size could still have massive errors depending on how unstable our differential equation is. So here we have, and once again, the way we could compute this if we were doing this by hand just to see how this would work, this is for delta t equals 1. This is delta t equals 1 right here. And the way we would compute these estimates is, again, to build our table and get our dy dt in here. And so at time 0, we have a y value of 10. The dy dt in this case depends on both the y value and the t value, so I take 0.2 times 10 minus t, which is 0, and that gives me 2. So because my time step is 1, remember now the change in y is going to equal the change in time multiplied by the slope at that instant. So because I'm looking at 1 year, multiplying that by 2 elk per 1 year, if that were the case and that's what we were dealing with, then we would get exactly 1 more elk as our change in y. So at time 1, we would estimate 11 elk, and then we would repeat this again, 0.2 times 11, but now minus 1. That would give me 2.2, minus 1 would give me 1.1. So in this case, our rate of change is actually getting smaller. And now I would take 1 year, multiply it by 1.1 elk per 1 year, and clearly in that case we're just going to get 1.1 elk. I'm sorry, this should have been 2 elk here, back here. Okay, there we go. And so we can repeat this for regardless of what the step size is. But this is telling me that at time 10, right here, my estimate of y is negative 17.876. If I compare that to a delta t of 0.1, and the way you know that is because it took 100 time steps to get to time 10, 0.1, 0.2, 0.3, 0.4, all the way counting up to time 10. And now my new estimate is negative 33.67. So you can see from here to here, that's a big change, right? That's a massive change. Now I know that this one is more accurate, right? So delta t equals 0.1 is more accurate. I don't know how accurate it is, but I know it's more accurate than delta t equals 1, right? It's more accurate than. So instead of coming up with an exact value, which we don't have, we're going to kind of treat this as it's approximately exact. Okay, right? Because it's more exact than the delta t equals 1. So what I'm going to do is I'm going to do my y estimate for a delta t of 1. That's my estimated value at time 10, minus my y value for a delta t of 0.1. I'm just going to use this subscript here at time 10. You know what? Maybe I should be a little bit more cautious here. Let's do delta t equals 1 at time 10 minus the y value for delta t equals 0.1 at time 10, and then divided by the more exact of the two values, which is the y value for delta t equals 0.1 at time 10. So that's going to give me the delta t at time 10 is negative 17.87 or 88, and I need to multiply this by 100 to get a percentage, minus negative 33.67 divided by negative 33.67 times 100. So I'm just doing this off to my calculator here. Which comes out to about negative 46.9%. Okay, that's huge, right? That's a huge change in the estimate from one step size to the next. Now, if I compare it to this next decrease in step size, which is delta t equals 0.01, and you can see that now it's requiring 10 times more computations because I cut the step size into tenths, and now my estimate is this value here. I'm going to spare all the notation here, and so I know that my estimate, or the less exact of the two estimates, is the negative 33.67 minus the more exact one, which is negative 35.61, divided by the more exact of the two, multiplied by 100. So now I come up with negative 5.45%. So we're still below, right? These mean that our estimates are underestimates. And we're still improving pretty significantly from delta t equals 0.1 to delta t equals 0.01. That's a pretty still big improvement, that 5.45%. I'm sorry, I don't want to make these appear linked together. So the change in value from delta t equals 0.1 to delta t equals 0.01, we're about 5. This estimate is about 5%. Yes, I'm sorry. So this estimate is about 5.5% under the more exact estimate. So it seems like there's still room for improvement here. We said that we wanted to get that error to be smaller than 0.9%. So we're at 5.45%. We're not quite there yet. Now, one of the things you may notice with using this applet is that if you try to decrease the step size too much for some functions, unless you have a paid version of the software, it may not necessarily produce what you're looking for. So this guy here does not want to, it'll show me some information, but it doesn't want to print the table for me. It says I'm out of computation time. I, at that point, would like to default to another piece of software. So this equation here, I'm actually using a different piece of software. That's this one. You can find many of them on the web. So this one in particular allows you to input your differential equation y prime, but you have to use y and x. Initial time is 0, initial y is 10. Point of approximation, this is what value of time we want it to compute up until. This is the step size, and then if you know the exact solution, you can type it in here. But we just go ahead and calculate, and it gives me an estimated y at time 10 of negative 35 point something. So here we go, right there. Time 10, it's not letting me get up against it, but about negative 35.881. So in this case, if I now look at the change in my estimate, I can see that it has not changed very much, right? It went from here to here. So the more approximate of the two is we want to do estimated, which is negative 35.61, minus the more exact one, which is negative 35.81, divided by negative 35.81. So notice how our exact, quote-unquote exact value keeps changing, because what we're treating to be the more exact value is the one that was computed with the smaller step size. And this comes out to about negative 0.56%. Now, so the change in precision, we were only in terms of these two errors, these two values, the error, this value, this negative 35.61, was just under, or just over 0.5% smaller than this negative 35.81. Now, we wanted to keep estimating until we were certain that our relative error from step size to step size was smaller than 0.9%, and this is smaller than 0.9%. So since the change in precision was less than threshold of 0.9%, we estimate that y of 10, and maybe down here I'll just say that this was for delta t of 0.001, that our estimate is about negative 35.81. And it doesn't matter that it's negative. We're not necessarily dealing with ELK here. This is just a differential equation that we're trying to solve. And now, how close are we to the exact solution? Well, we can't tell from this, right? But we know that by decreasing the step size even more, the relative error is going to get even smaller and smaller. So you kind of have to set your threshold. I chose 0.9% arbitrarily. I didn't want to use 1% because we have all these 0.1s floating around and 0.01, so I just chose 0.9%. Now, it turns out that we can solve this differential equation using a method that we'll later establish. And by the way, the exact solution to this differential equation is negative 35.8358. So check out our approximation here. We're very, very close. So this relative error analysis, by decreasing the step size and comparing adjacent estimates, is actually seems to be a pretty good way for this, at least for this function, a pretty good way for me to hone in on what that exact solution is. There are other better methods than Euler's. There's something called improved Euler's and the Runge-Kutta method. We will take a look at those in the next lesson.